today by...
Just a second, sir. Recording.
Thank you. Okay, so let's begin today by continuing our application lecture on COVID-19. And really, it's, it's essentially an excuse for us to present some of the core concepts that will come up repeatedly in your study of data science. So on the lecture from now, I suppose almost 2 weeks ago, we basically just did a hit and run introduction of all of these concepts, the frequentist views of probability, things like estimators and bias. I advise you, I recommend that you go back and take a look at the first lecture of this two-part series on, on this two-part special applications topic on COVID-19. Next week, Ramiz will begin his lectures on fraud detection. That should take another 2 lectures. And then after that, I will cover election polling as another application lecture. And all of these applications end up covering all of the concepts that we want you to have had an introduction of. Okay, so don't think that this is the most thorough introduction, because each one of these topics we can spend a lot of time discussing. So the purpose of these introductory lectures was just to give you exposure to what's out there in a way that should be self-contained and understandable, so that you can then understand what you really need to go and master the stuff at the most advanced levels, for which we will also prepare modules and help you prepare. If you haven't seen on the Google Classrooms, we have now added some more material. So the problem set that we covered on last Wednesday's sort of I'm not sure what to call it. It wasn't a lecture. It was just sort of a trial of the Google Classroom format. The problem set and the solutions are up. Some of you have been asking for more resources, so I have included a link in the useful links. So at the top of the if you click on the Classroom tab when you enter Google Classroom, at the top there'll be a useful links tab, and you should open it up. And there are some additional links now appearing to an MIT course. MIT is short for the Massachusetts Institute of Technology. It is one of the world's premier research institutes for many technical subjects and more. And one of the things that they've been a pioneer in for now at least a decade is putting all of their courses online for free for everybody. So I found a course where it appears to begin with a lot of similar topics to what we are covering here. However, they do assume knowledge of calculus, which is something that we don't assume in our lectures. So some of the things you will find, if you don't understand calculus, you're not going to be able to interface. But nevertheless, there are live lectures, there are lecture notes, and there are problem sets. So I encourage you to go there and take a look. If there's anything that you find that you would like more details over. What I have checked, however, is that certainly it's not very different from what we've covered. So in some sense, I'm quite pleased that the pedagogy we're using has been tried and worked in another context. The only disclaimer is, if you don't understand anything in that course or you're having trouble, don't worry. I only put it up there because somebody asked me to, or several people asked me to put up more material. The goal of this course is to be here to sort of make it understandable. And again, I stress, if you're having difficulties with the material, please contact us. But what you shouldn't do is stare at these lectures, look at the words, go away, and come back and say you don't understand them, because what you really need to do to understand all of this stuff, like everything in life, is to practice. You have to really spend a lot of time practicing and thinking about this stuff. And the way we hope to have presented it is that you should not need to leave the, you should not need to use any other resources other than what we provide to reach a level of understanding of this subject, which is, sufficient enough to get the basic ideas and to do some basic computations. And in the next module, we will obviously begin with hands-on applications. And and so you will see these things. So you will, if you don't master them in this introductory module, you'll master them out of practice in the next one. So, so of all the concepts, so this is, in the last lecture, this is actually quite a lot. Okay, so these are some of the most recurring and profound ideas in statistics and statistical inference and data analysis. And of course, we ended up with Bayes' theorem, and it seemed like a funny manipulation of certain quantities when we're dealing with conditional probabilities. And today's lecture will develop them and apply them to COVID-19. And so if you're finding these lectures maybe a little too slow for you, I strongly advise that you pay careful attention now, because as you will sometimes find in these lectures, it starts out simple, and then within 3 slides, you're dealing with something really, really complicated. But still simple, but the implications are very, very deep. So I'm just going to remind everybody, or if you haven't yet seen the first lecture, maybe this is a quick introduction, is that very often we're dealing with situations where we have multiple occurrences or more than one random variable. And we encounter the phenomenon of what is called conditional probability. So you can have 2 different events, and you may ask, what is the probability that both those events occur? So what is the probability that you roll you're rolling 2 dice, and one dice rolls a 6 and another one rolls a 2, or if you have a dice and a coin, and one dice rolls a 6 and you flip the coin and you get a heads. Because those 2 occurrences are independent, just like consecutive coin flips, then it doesn't matter what order you do them in. In fact, the outcome of one does not affect the outcome of the other at all. It is completely independent. So the joint probability, the probability of both events occurring, is just a product of the probabilities. Okay, so we had, at the end of our last problem set, we went through some examples. And if you went through that, you would understand that for a deck of cards, subsequent events are no longer independent, because once you once you remove an element from, once you remove a card from a deck of cards, there's one less card. Okay, so if you ask what is the probability of finding any queen followed by any 4 of any suit, then the probability of pulling a queen from a fresh deck of cards is 4 out of 52. But now there's 51 cards left. Okay, so these 2 probabilities are no longer obtained by the independent probabilities of just joining them one after another. So these probabilities are not the joint probability, the probability of getting both events, is not equal to the product of the probability. So this is what we view as the conditional probabilities. Of course, if we have 2 independent deck of cards, we have 2 separate decks of cards, and we do the same thing, then of course this is true again. But yes, so that's the idea of conditional probability. So so in order to deal with it, what we do is we just say, well, obviously, if 2 things are to happen, then the probability of both of them happening must be given by the probability that one of them has happened, let's say x, given that y has happened, times the probability that y has happened. So this is just a definition, if you like. But this must also equal the opposite, right? That if both events have happened, then it could have been, the other way around. That you should have, it should be the probability that y has happened, given that x has happened. So we're taking x as a certainty and calculating the probability that y has happened, given that x is a certainty, then multiplying by the probability of obtaining x. So setting these 2 quantities equal to each other, as we do here, and we just divide, let's say we set this equal to this, and we divide by p sub y, you end up with this following expression, which is known as Bayes' theorem. So we are going to use this to calculate the probability. We're going to use this to do a lot of things, actually. But let's begin by first using it to calculate the probability that you're infected with COVID, given that you've tested positive. And as I've been advertising, the answer is quite surprising. And well, it's actually well, yes, indeed, it is surprising. It's not intuitive to most people, including myself, including anybody. This type of Bayesian reasoning is something that is not, if you like, it's not obvious if you're used to interpreting probabilities as a frequency. And so, what we've seen here is, just divide, just taking definitions and equating them to each other. It gets the name of a theorem, but really it's a tautology. So tautology means something that is obviously true. It's not saying anything. It's just saying something. It's like saying, the sun is hot, right? I mean, that's what a tautology is. It almost follows by definition. So, okay, so this is where it really begins, and this is what we're going to exploit is Bayes' theorem. Okay, so the question is, what is the probability that you're infected with COVID? Let's say that's the probability that you're positive, or that you're infected with COVID, given that you've tested positive. Okay, that's what we're trying to figure out. So before we get into that, we realize that all medical tests actually have two numbers that determine their effectiveness. So it parameterizes their efficiency. The first one is called the test sensitivity. So that's the probability that a test returns a positive result given that a patient is actually infected. Okay, so that means that if you are indeed infected, what is the probability that you get a positive result? It's not always true that you get a positive result if you're tested infected, right? And the other one, it's a slightly different number, is called the test specificity. It's an independent number. You should think about it and convince yourselves that these are two separate things. Okay, and that's the probability that a healthy patient will indeed test negative. Okay, so that's the probability that you will get a negative test given that you are actually negative, so you're healthy. So the notation we're using here and what follows is this little squiggle, which in mathematics is used to denote not the following. Okay, so it's in logic. It's a symbol used in formal logic, and if you see something that says squiggle times something, it is negating it. It is saying that this is not true. Okay, so this is the probability that you test negative given that you are not infected. Okay, so for PCR tests, so polymerase chain reaction tests, these are the gold standard today in COVID and HIV and all virus testing mechanisms. So if you don't know what a PCR test is, what it does is it essentially takes a sample of blood or something, anything with where you're going to have some viral material, but it comes with lots and lots of other stuff. Okay, so when you have the cotton buds going up your nose or down your throat for a COVID test, they're just collecting saliva or mucus, and they're putting it in a machine, and then it induces this thing called a polymerase chain reaction. So what that does is it looks for specific things with specific characteristics, that is DNA, and once it finds them, it basically amplifies them, and it amplifies them, so it makes the amount of it visible, more, and you do that by heating up a sample to make that reaction more and more, and then you take that sample with that thing amplified, and you repeat and repeat and repeat. Go through many cycles. Okay, so even for the best PCR tests, the test sensitivity is not 100%. In fact, it's impossible to get 100%. It's somewhere between 0.7 and 0.95. Okay, so that's saying that the probability that you test positive, given that you're infected, is somewhere between 0.7 and 0.95. So depending on the test means, depending on how good the equipment is, depending on how many times you do the cycle of going, heating up the sample up and down. Usually they take somewhere between 10 and 30, depending on how much viral load that they're dealing with. And moreover, you might ask the question, why don't they just do that an infinite number of times and just get a 100% accurate result? Well, the problem is then you will end up getting many false positives, because if you've ever had a blood test for anything, let's say you get a blood test for, I don't know, some disease you have no chance of having, and the blood test comes back with some tiny number, right? And then it says negative, and it's just like, well, there's a tiny number there. Do I have that disease? And the answer is no. That's part of the statistical noise of the system. Okay, there will always be some particles maybe left over from a previous test, or maybe there's going to be some, so you can't ever get 100% sensitivity simply because then everybody tests positive for everything, right? So it's not useful to have 100% sensitivity. So the test sensitivity is between 0.7 and 0.95, and that's for a really good test. Okay. Then there's the other number, which is test specificity, which is the probability that a healthy person tests negative, and that tends to be a lot better, and it's typically 0.95. So I looked these numbers up from some medical literature for the types of tests that they use in India, say, and okay, these are the two numbers. So imagine you're a lab technician, and somebody tests positive for COVID-19. Okay, so what is the probability that this person actually has COVID? Okay, so since this test is not perfect, as we have discovered, this is not a certainty. Okay, a positive test does not necessarily mean that you have COVID. So let's just apply Bayes' theorem. Okay, so Bayes' theorem in this context says that the probability that you are indeed infected given a positive test is given by the probability that you test positive given that you're infected times the probability that you're infected divided by the probability that you're positive. Okay, so just bring this over here to this side and convince yourselves that indeed this is just Bayes' theorem. This is just the tautology now written down in equation form. Okay. Now, furthermore, suppose there is some actual prevalence in some locality that somebody can measure by some other means. So let's just say I state for you that right now the probability of the average person being infected is 0.01. Okay, so in some locality, let's say in Varda. So in Varda locality right now, 1 out of 100 people currently is infected with COVID. I'm making that number up. Okay, but let's just say that's true. That's still a lot of people. Okay, still a lot of people. But not that many, right? I mean, it's still that's still 1%. Typically during flu season, in the rainy season in India, there's many cold. This is an average infection number for a very bad disease. That's obviously not hit epidemic proportions. Okay, so if we say that just somehow we assume, or let's say somebody tells us that only 1% of the population is currently infected. So we have this number up here, and moreover, the probability that you test positive, given that you're infected, is indeed the test sensitivity. So let's take that to be 0.95. Let's take the best case scenario and say that this number is 0.95. All that's left to figure out is the probability that indeed you test positive. Okay, but we can calculate that number. We have to think a little bit, but we realize that the probability that you test positive can only be two things, right? Either you're infected and you test positive, or you're not infected and you test positive. Okay, I hope that's obvious. Okay, the probability that anybody tests positive is given by the probability that they're infected times the probability that they test positive given that they're infected, or they're not infected, times the probability that they test positive given that they're not infected. There can be no other possibility. Either you're infected or you're not infected. Okay, so if either of those probabilities are true, what is the probability that you test positive? So that's given by this quantity. Okay, so what we can do is we can substitute this into this equation, right? And realize that if I just substitute this into the denominator here, notice that this term is common Okay, so now we have these two terms in the denominator, but this term is common to this term. So I can just divide through by this term, and I end up with the following expression. Okay, this is all, this is starting to get complicated, but it's all very, very elementary, right? It's all very, very straightforward. Okay, so think about what you know by a conditional probability. Think about the card game, about what these probabilities mean. All of that follows from these simple definitions. Okay, I could explain this to somebody in 8th standard, in 7th standard. Okay, this doesn't need any complicated mathematics. And then I divide through by. Okay, so I just realized that the probability test positive is given by this. There's only two possibilities, and I just throw it in and I simplify the equation. Okay, so we know what the probability of being infected is, and we know what the test sensitivity is, which is these two numbers. Okay, but we know that the probability of not being infected is simply 1 minus the probability of being infected. Okay, so we know now what this factor is. We know what this factor is. We know what this factor is. It's just the test sensitivity. So we're just left to figure out what this factor is, which is the probability that you test positive given that you're not infected. So it's which is the probability of a false positive. Okay, so probability of a false positive is given by 1 minus the probability that you test negative given that you're not infected. Okay, and this is the test specificity. Okay, so we know that this number is 0.95. So after all of that, okay, all of this just follows from definitions. Okay, I've done nothing other than manipulate some elementary definitions. So finally, we can calculate now. The probability that you indeed are infected, given the results of a positive test, are given by this formula. We just applied Bayes theorem. 1 minus the test specificity times 1 minus the prevalence times the sensitivity times the prevalence. You add that to 1, and you divide the whole thing by, you take 1 over the whole thing. Okay, so let's put in some numbers. Okay, so again, we said that we chose the best case scenario for the sensitivity, which is 0.95. In general, this number is somewhere between 0.7 and 0.95. And we have the prevalence, let's say, in society of 0.1. So one out of 100 people is infected. So if you put in these 3 numbers into this formula, then the probability that you're indeed infected, given the positive test result, is only 16%. Okay, so if you're in a lab, somebody tests positive, you know that there's 1% prevalence of COVID-19 out there, then there's an 84% chance that this person is not really infected. Okay, so that's pretty interesting, right? So you have to compare this number to the 5% false positivity rate. So if you had just that number in your mind, then you would maybe have this false impression that only 5% of tests would test positive if the person wasn't infected. It's not true. Okay, what you've done is you've not really interpreted probability correctly by just going by that number. By simple application of Bayes theorem, it has allowed us to overcome one of the biggest fallacies that occur when you misinterpret probabilities as an occurrence. Okay, so if there is only a true prevalence of 1% and your test has a 5% false positivity rate and a 5% false positivity rate and a sensitivity of 0.95, then a positive test result is only indicates that you have is only indicating that you have a disease. You really have the disease 16% of the time. So, yikes! That's saying that 1 out of 6 people, 5 people are going to test positive and they're not going to be actually infected. So that's a bit annoying. So what do we do? Well, let's first pause and consider what one needs in order to really understand what's happening. So it's only when this test specificity is 100%, which is never true in reality. And in fact, we don't want it to be true in reality because because there's always going to be lots of noise. There's going to be, tests will always, you can't have tests infinitely sensitive because otherwise, we'll test positive for everything. We can go tomorrow and we'll get, this, because there's always going to be random noise in the instruments. So you'll never test, the test specificity will never be 100%, but only if somehow one could design it is the probability that you're infected given a positive test result really equal to certainty. Okay, because we want this number to equal 1 in that case, and that's only true when the test specificity is either 100% or the population prevalence is 100%, which is telling you no information because that's saying that everybody has COVID. So why bother testing? So just to give you some indication is that even with a 99.9% accurate test, both for specificity and sensitivity, with 1% prevalence, you can still only be 90% sure that somebody who tests positive will indeed have COVID. So 1 in 10 positive tests will not have COVID, even with these unrealistically accurate tests. So what do we do? Okay, so we test again, actually. But what happens now is it is no longer true that the population. So now that you've done that test once, it's no longer true that you're in the general population. Now you're in the population subsample that has tested positive. Okay, so now you're in that subsample who are truly positive, who are truly infected, given the positive test. Okay, so now that's 16%, right? So we've done this once, okay, and found that that the probability that you're really infected, given the positive test result, is 16%. So now you're in a population where 16% of all of the people with positive tests are indeed infected. Okay. So we just do it again. We just do another test. Okay, but now prevalence is 0.16. It's no longer 0.01. And for the same test specificity and sensitivities, 0.95, after 2 consecutive tests, that probability goes up a lot. It is now 78%. So 78% of people who have 2 consecutive positive test results are indeed infected. But that's still not good enough. I mean, that's still 22% of people that that are left over that aren't infected given a positive test result. So what do? We do it again. Okay, but now the prevalence for the new subsample is the people who tested positive twice, of whom 78% are actually positive. So if we repeat this formula one more time for a third test, but now where prevalence is 0.78, now we're getting up to 0.986. Okay, but if you think that's certain, let me ask you the following question. Let's say you go into the hospital and you get a cancer test. And let's say I did this for cancer instead of COVID-19. 0.986 is still leaving 14 people out of 1,000 with a false diagnosis. Okay? So, and considering that the treatment for cancer is usually chemotherapy, which can often kill you if you're healthy, that means you're killing 14 people out of 1,000 for nothing, right? If you've made a misdiagnosis. So if you think this number is impressive, I invite you to consider that it really depends on what you're talking about here. So considering that the treatment for COVID is not going to kill you, well, at least if you follow the recommended treatments by the Indian government, it's not going to kill you. If you followed some of Donald Trump's recommended treatments, they may have killed you. You certainly want to be a bit more sure than 0.986. Okay, so we use this in the example of COVID, but for other things like a cancer diagnosis, you really want to be more precise. And so we do a test. So this is not good enough. We want to be more than 99% sure. So in order to be, so this is not yet there. So what we do is we now repeat the test again. The test, of course, is the same specificity as before, 0.95. The sensitivity is the same as before, 0.95. Now we put in 0.986. And indeed, after 4 consecutive tests, only 1 out of 1,000 people will not have COVID after 4 positive tests. Okay? So this is one of the most profound, useful applications of Bayesian reasoning in medical diagnostics. And I want to take a minute here for you to talk to you personally about how you should approach any situation where a doctor tells you anything. Okay, because this is probably going to happen in your lives, in the lives of the loved ones of your family. Okay, a lot of doctors aren't aware of this, and this is a problem. Okay, let's go back to this example here. Okay, so in fact, let's try something else. Let's try something else. Okay, let me just stop here. Let me do the following thing. Let me just share with you. So what I've done is I've just taken this. Can you see my? Can you see this little notebook here? Can you see this little mathematical formula? Is this visible? Sorry, I just can't tell if you can
yes.
see it.
Yes, sir. Yes, sir.
Okay. Okay. Now, let's just really take home the life and death nature of this observation. Okay, because cancer is everywhere. Okay, it is very likely that somebody you know one day will have cancer. Okay, and so let's imagine a cancer diagnostic is, I don't know, 97% accurate. Okay, and let's say the specificity is it only gives 1% false positive. And let's say indeed the prevalence is only 1% in the population. Okay, so you go to the doctor. Okay, and this is you go to the doctor, and the doctor says your family member has cancer. There's only a 1 in 2 chance that they really have cancer if they only did one test. Okay, so you must get a second opinion. Okay, when you get a second opinion, you do the test again. Okay, then there's a 2%. Then there's a 98% chance that your family member has cancer. Okay, and so at that point, probably you don't really want to get a third opinion, but this is just letting you know that we end up, maybe not in India, but in the West, we end up killing more people by trying to over-test for cancer than curing them for a lot of diseases. Okay, so when doctors, and this is partly because of the way the capitalism works in some countries, insurance companies charge a lot of money. Well, certain people try to charge a lot of, try to gain a lot of profit via the way the medical care system is set up by over testing people, and lots of people are told from a certain age. I think anybody who's a man who's over 35 is told to go to the doctor once a year to have their prostate gland examined, which is quite invasive. So unless you go to a very fancy doctor and they do it by ultrasound, of course nobody does it, right? But were you to do that, chances are you're going to get a false diagnosis more often than you're not. Now, the treatment for prostate cancer is pretty fine, so there's no ill consequences of it. But let's say it's pancreatic cancer, and the treatment for that is immediate chemotherapy. Chemotherapy is more likely to kill you if you're healthy than to cure you if you have cancer. Okay, so you have to be very, very careful about how to interpret these things. And so anybody you know ever gets a cancer diagnosis, do not listen to the doctor. Listen to 2 doctors. Okay, you must get a second opinion. Never, ever only get one opinion. Okay, and you now know this because you have taken this course at Nalanda Academy, and you've understood Bayesian reasoning, and you understand why. Okay, it's not just that I'm telling you this. You can go away and just go back, start from the beginning of this slide. Okay, start from the beginning of this. Look, this is not magic. I'm showing you something that puts you ahead of 95% of doctors in the world. Okay, not all doctors are this stupid, but some of them are. Okay, and so this is part of why we're not just interested in telling you to just learn a bunch of random facts so you can enter some course. We're teaching you this stuff to apply it to your daily life and to become better skeptics and critics of the information you have around you. Okay, and this is probably one of the most direct applications of Bayes' theorem that is 100% relevant to everybody's life. Okay, whenever I have a family member and they come back and they said blah blah blah, tested positive for cancer, I always say go test it again. Luckily, in my family, very few people have tested positive for cancer. I'm from farmers, so we're all very healthy people. We we eat very healthy. We all we're descended from people that have been farming the land for generations. So we don't have very much cancer in our family. But I think for a lot of Indian people who move from rural areas to the cities, the change in lifestyle has meant that, they've gone lots of money, and they think having money means we should eat well and, enjoy our lives. And this is causing lots of things to come up in India, a lot of lifestyle diseases. And so, lots of things like cancer are much more prevalent now. So let's get back to COVID-19. But that's what I wanted to really emphasize, okay, is that the positive medical diagnostic is almost never a true indication that you have the disease, unless you repeat it again and again and again, okay? So, and by the way, why is this more relevant for cancer than something like COVID-19? Because when COVID-19, by the way, this is exactly what they do in the laboratory, right? When they get a COVID-19 test, they just repeat the test again and again and again, because they can. It costs them a bit more money, but it's not that difficult. Whereas with a cancer diagnostic, you can't just repeat the test, because what if that test involves going inside, cutting open your body, going inside and scraping off some tissue, right? That is not a test you can keep doing again and again and again. It gets a little painful and expensive, right? So this is why you need to ask questions from the doctor. How was this test done? What is it, and really inform yourselves, and always get a second opinion with a cancer diagnosis. Okay. But nevertheless, for COVID-19, you indeed have the case where if you have a 1% population prevalence, as we've seen, we indeed have a probability of 4 consecutive positive tests, indeed using the probability that only 1 out of 1,000 people are going to not be infected with 4 positive test results. Okay, so that was that situation. But now imagine another situation, which is now we're in a very bad stage of the pandemic. Okay, so 1% is like, it's an okay stage of the pandemic. But let's say we're in a very bad stage, and in some locality, the prevalence is about 30%. Okay, so at the height of the first wave, and by the way, this is the prevalence of currently infected individuals. Okay, so you can have many, many people. Let's say 60% of the population has been infected over some wave, but at any given time, it's going to be a much smaller fraction. So a prevalence of about 30% is really, that's saying 1 out of 3 people is currently infected. This is a very, very bad stage of the pandemic. Okay, so this is only going to be true within some locality, right? So let's say within on a cruise ship, if you're stuck on a cruise ship, or let's say in a school, or, in some housing estate, or some slum, right? These are reasonable numbers within a particular locality. So with the same test sensitivity and specificity, okay, so the tests haven't changed. They're still 0.95 specific and 0.95 sensitive. Then with a prevalence of 30%, a single positive test tells you that you're 89. If you just put in these numbers, okay, it tells you that you're 89% likely to have COVID. If you test positive. And after 2 tests, okay, it's 0.994. So it only takes 2 tests to be more than 99% sure that somebody is actually infected given a positive result, compared to when the prevalence was only 1%, where it took 4. Okay? So in some sense, in a country like India, with limited resources and huge differences in access to healthcare, across different parts of the country, across different localities, what would be the right testing strategy at the start of the epidemic? Well, really, testing at the beginning of the epidemic is, as we've seen, potentially a humongous waste of resources, right? If you need more than 4 tests to become more than 99.9% sure that somebody has COVID, of course, they don't go that high. They usually only care about 98%. Even then, you needed 3 tests, whereas you probably only needed like 2 in the middle of the pandemic. It's not very useful, right? So mass testing at the beginning of the pandemic is not necessarily a good idea unless you're going into targeted localities where there are lots of cases. So indeed, at the beginning of the pandemic, especially if you lived outside of India, the ICMR, the Indian Council for Medical Research, was getting a lot of criticism for not testing enough. But in reality, the people there were actually pretty smart, and maybe they made the right decision because they knew there's no point, right? And that you're just wasting tests. And that the way to really use tests is to just go into localities where you know the prevalence is much higher. There's no point just pulling some random person off the street and testing them, because you're going to waste a lot of resources, which at the time, at the beginning, were very finite, because it took some time for people to build up the capacity to mass test. So good. So that was the first question that we looked to answer, which is, what is the probability that indeed you are infected given a positive test? So I hope you understand that there is power to this type of reasoning. This is not just some stupid mathematics that I'm torturing you with because I like to make students suffer. I definitely don't. Okay, so good. So let's move on to another more interesting question right now, which is, I told you at the beginning that let's say that there's some prevalence out there of 1%, 1 out of 100%, 1 out of 100 people is currently infected. So how can we actually estimate that? Let's say that's the quantity we're interested in, okay? So I just go back to Bayes' theorem, right? But instead of calculating this quantity, I just flip it around, right? I want to calculate this, so I just bring this over here and divide by this, and so this is just manipulating Bayes' equation. Okay, there's a lot. Therein lies the power of Bayes' theorem, right? Is that it's a very simple equation, but the way you interpret it opens many doors to answer many different hypotheses that you thought you never had the chance of testing before. And something that we will not cover in this module, but we will certainly cover in the future modules, is this thing called hypothesis testing, which is also very important. I mean, maybe Ramiz will cover it in his next lecture, but I'm not sure he'll do it in the Bayesian way. So there's this thing called Bayesian hypothesis testing, which is taking probability and turning it around from the thing, an observation of frequencies, but degrees of confidence. This hypothesis is true to X% confidence. That is something that people use a lot in statistical inference, and this is really where the power of Bayesian reasoning comes in. But even if you don't do that, I hope to show you that there's still a lot of really powerful stuff you can do. And one of them is just being able to answer many questions. So the question that we're interested in now is, how do we estimate the number of people that are infected out there? Okay. So okay. So with a known test sensitivity, right, which is this is a fixed number, which is the probability that an infected person indeed tests positive, which is just some number on the side of the test, it's 0.95. And if you have some way of determining the probability that you are infected given a positive test, we can determine the population prevalence via an estimate. Okay, this is the keyword, an estimate of the number of positive, the proportion of positive, of the people who test positive through random sampling. Okay, so there's a lot of different concepts here. Let me break them down one by one. Okay, so imagine you go out and you just sample randomly some people, and you give them a PCR test, and you find that some fraction have tested positive. Okay, now we want to understand how much of that, we want to know what this number is. Okay, so the last question involved us calculating that number, and indeed it was not very easy. Okay, so in this case, but we were given this number in that last example. In this case, we now don't know that number. So in order to know this number, we need to know what this is. So how do we figure that out? So the idea is, you take some subsample. Let's say it's, I don't know, 10,000. It's certainly not the entire population. It's just some subsample. From that tiny subsample, indeed, you can take all of the people that have tested positive and subject them to some other testing, maybe some independent test, or maybe another, a set of repeated PCR tests to determine the true number of people that are infected given that positive subsample. Okay, and so that's certainly a lot more work, but it's a lot less work than doing that for the entire population. So it's still a small number of additional checks, but if you can somehow get this number from that subsample, or maybe you use another independent test, okay, not a PCR, but then another one that's just as accurate, but it uses a completely separate systematics. Systematics means method of doing things, so that there's the errors, the mistakes, or if you like, the uncertainties don't don't correlate. Okay, so what this means is, well, we'll explain it in future lectures. In some sense, it's an independent check. If we can somehow obtain that number, then knowing this number and knowing this number from that positive subsample, we can estimate the number of people out there with COVID by just doing a random sample. Okay. But first, we have to understand what it means for a sample to be truly random. So what that means is that any quantity you estimate from this sample. Okay, so the sample is not the whole population; it's some subset of the population. That any quantity you estimate from the sample will be very close to the true values you would estimate from the full population. Just like an election poll. Okay, in an election poll, you don't go and ask the entire country what they're going to vote because that's effectively running the election, right? The whole election. What you do is you ask a small number of people. So if a sample is truly random, then the quantity you estimate is getting close. Now, exactly how close depends on the size of the sample, but it's getting very, very close to the true value of the quantity. But it turns out that random sampling is very, very difficult in a country like India. So I want you to just now think about how you would even do such a random sampling in your locality. Think about it, okay? So let's say you wanted to ask people in your district, okay, who are they going to vote for? Okay, how are you going to do that? Think about it. Right? How? I mean, so in India, some people, live in, in colonies. Some people live in slums. Some people are homeless, right? Some people live in these shiny buildings. Some people live in defense colony. How are you going to do it, right? It's tricky. Okay, in some sense, you need to know the proportion of people that live in all of these different communities, and then draw the samples proportionally to them. But we only take census data once every 10 years, and I'm not sure if it's released with such local resolution that X people live in this colony, X people live in that colony, X, Y people live in this in these slums. You just don't have this information, so it's very, very difficult. Moreover, India is a very complicated country, right? I mean, even cities within India are universes, right? So here's a news article from July, earlier this year. It's from the National Herald, and some people were saying that that in Mumbai, that herd immunity was. What does herd immunity mean in the context of COVID? It means that enough people have been infected that they're basically immune, at least temporarily, such that if somebody else gets the disease and enters the community, they won't get to spread it because people don't get it and so they don't pass it on. And the reason is that they did what they called a zero surveillance study for COVID-19. So they went and they did what they thought was random testing for people in different parts of the city. And they said that 57% of the slum population and 16% of the non-slum population. And so for those of you who are familiar with Mumbai, you will know that the majority of Mumbaikars live in slums. And I actually hate this word in English because it has a very, very nasty and not nice connotation. These are just settlements where you have encroached upon land, and not all of them are necessarily bad places to live. Of course, they're not super great, but some of them it doesn't always mean the same thing, and it's used in a very, very negative way, I believe. But the majority of Mumbai's population lives in what they call a slum. Okay, more than 60%. So if almost 60% of 60% of the population has already had it, and 16% of the 40% that's left over, that's a lot of people, right? And so they're saying that maybe most Mumbaikars have had COVID already, so therefore are we close to herd immunity? Now immediately I went in and I looked at the samples that they looked at, and there are 2,000 widely separated slum settlements throughout Mumbai, a lot of the samples were from, for those of you familiar with Mumbai, they're from Chembur and in the Dadar area, like a little bit below. And I think the furthest north they went was it wasn't very far north, and Mumbai goes very, very far north. And most of my family members we live around the northern part of Mumbai. And so I was thinking, well, they didn't sample anybody there. There are plenty of slums there. And I, spoke to some family members who work in hospitals there, and they're like, yeah, we haven't seen too many outbreaks there. So by randomly sampling just a subsample of the slums, they've arrived at these ridiculous numbers, which can't be true. Okay. And I think we're seeing now in Mumbai that they were nowhere near herd immunity, right? I mean, obviously the epidemic is kicked off very, very fast again. So for reasons that are not poorly understood. So random sampling is very difficult. Okay. What they should have done. So how would you have done it then? How would you have done it? Is you would have understood what fraction of the population lives in which community, and devised a sample that is representative of those fractions. Okay. So and that's a lot of work, right? But unfortunately, it's not clear to me that people have done this work. But it's almost an impossible task, I would say, if you don't have completely accurate census data. So, it's fine. It's okay to make mistakes. I think a lot of people made mistakes in this pandemic. And so, it's the nature of how to make decisions based on incomplete information, and that's what we're here to learn. Okay, so this is part of the one of the skill sets that we want to convey to you is how to reason with incomplete information. That's one of the things that we really need. That is actually quite funny. That very few people, including scientists, know how to do well. So if you know how to do it well, you are smarter than 99% of the scientists out there. And one of the easiest ways to explain this is in the West. It's really quite stupid, actually. I'm really angry at how dumb Westerners can be, because unlike us Indians, well, we think we're very smart too, which can be a problem. But Westerners have this arrogance that they all think that they're smart, and it's a bad thing, because most of us are stupid, including myself and Ramiz. We're not, nobody can know everything, and there's a big opposition to wearing masks. And so at the beginning of the pandemic, people were asking, well, where's the proof? Where's the studies that show that wearing masks are effective? Fine. We didn't have them yet. And in fact, depending on the study, the data is a bit noisy. So it's not clear that they actually make a difference, at least at the level of these studies. However, from experience, we know that countries that do adopt it, and just from common sense, if it's a respiratory disease and you're, keeping in things that could spread it, it's probably a good idea. So what we also have to get good at doing is understanding the different stakes that certain decisions have. So if there is a probability, if there's an uncertainty to whether masks are effective or not, there's an asymmetry at work as to whether you lose anything by wearing a mask. Okay, so if I wear a mask, it's not going to cause that much harm to anybody's health, including mine. Whereas if I don't wear a mask, it's potentially quite harmful. So there's an asymmetry that people haven't reasoned through. Okay, so even in the absence of strong evidence, it doesn't hurt to put on a mask. So put on a mask, right? If it turns out later that it doesn't work, then so what? Okay, we didn't lose anything. But if the stakes are the opposite, right, which is that, well, by not wearing a mask, you're probably going to make the epidemic much worse. You see how those two things are asymmetric. And something that people are only now realizing in the last month or two is that, remember at the start of the epidemic, we were all told to wash our hands all the time because COVID can really be, there's still no conclusive evidence that COVID is efficiently spread by touching things. It is primarily, the only evidence we strongly have is through respiratory thing. Yet all of us washed our hands still. Why? Because it doesn't hurt. And in fact, the advantages of that is that it prevents other diseases from spreading. And what small chance of getting COVID that you have also goes away. Okay? So, and again, it doesn't hurt to wash your hands all that often, so why not do it? So, part of the skill sets that you have when you really understand probability and is that you can assign risks. You can assign in your own mind a risk factor to making certain decisions, which is what we're trying to also get you to feel confident doing by understanding how to use and how to think about probabilities. So good. So let's continue. And
sir, excuse me. Excuse me.
Yes.
Sir,
Yes.
can I ask question?
Of course.
Sir, is this the reason to be having a sample random, that we should have a normal probability distribution? That's the reason, or it is something else that
Not.
we should have random sampling?
They're separate things, but indeed, if you have an underlying normal distribution, you will find that the sample size you need is not very big. So in fact, no, it's not. To answer your question, is they're not strictly the same thing. They're very different things. But if you have a normal distribution, then the random samples you need can be quite small. If your distribution is not normal, in fact, if it has very, very extreme fluctuations, then the sample size has to go up very, very quickly. Okay, you are liable to misestimate the underlying thing, the underlying distribution, if the underlying sample is not normal. So sampling has an error associated with it. If the underlying distribution is normal, that error is some number for a given sample size. If it's a different distribution, it's a different error given a different sample size. So logically, they're two separate concepts. Is that clear?
So, okay, so why do we need a random sampling? I mean, we can collect in, as per convenience. We can go to collect sample or something the way we want. So,
Okay, so
how
let's go
does
back to
that
this example
change?
here. Let's go back to this example. Okay, so why do we need random sampling? Okay, so don't do random sampling. Just go to one building, collect all the samples there, and go away. Is that an accurate sample of and let's say you go into one building and you collect samples from all the people in one building and you find 80% of them have COVID. Will you say then that Mumbai has 80% COVID? That's my
No,
question. Exactly. Why? Can you tell me
no,
why
sir.
that's not true? So why do you think that's not true?
I mean, one building is that is too much, but because that doesn't represent the whole Mumbai.
Exactly. Perfect, right?
But I am
So
saying as
yeah.
per convenience,
So as
as per
what?
convenience, like 10 people from here, 6 people from somewhere else. I mean, if
But how do you know that's random
if
enough?
we are not able to exactly pick randomly,
So how do you know? But how do you know that's random enough? Is my question,
so how would that? I
right?
mean, what is the need?
Yeah. Okay. So that's why I mentioned that it was indeed quite hard. But let's say you wanted to do it perfectly. How would you do it? Okay. So let's say you knew in your locality the fraction of populations that live in this building or in this locality. Let's say you live in some village where 10% of the people live in a slum, 80% of village people live in houses, and 10% of people live in some railway colony. Okay. So to get a truly random sample, then you sample your sample should have 10% from the slum, 10% from the railway colony, and 80% from the villages. And that can only be so if you have a sample of only 100, let's say the village is, I don't know, 2,000 people, and you only get a sample of 100 people, provided those 100 are within that fraction, you probably have a good enough random sample, right? But if your random sample was 80% of people from the railway colony and 10% of people from the village, from the houses, you'd have your sample is not representative. I hope that's intuitively clear. Does that make sense?
Okay, sir. Okay,
No, but is it clear or should I try again?
okay, sir. Try again.
Yeah. Okay. So please think of this with me. Okay. Let's say you have a village where 80% of the people live in houses, 10% of people live in a slum, okay, Zopatpatti or something, and 10% of people live in some railway colony, okay, because there's some train station. So the fraction of people is 10% in a slum, 10% in a railway colony, 80% people live in houses. What I'm saying is, if you want to do a random, if you want your sample to be truly representative of the village, let's say the village is 2,000 people, then let's say your sample is only 100, then it's probably a good idea to get 10% of that sample from the slum, Zopatpatti, 10% of the sample from the railway colony, and the remaining 80% of the sample from the villages, because that's representative of the population in the village, right? But if you did some other, as you say, per convenience, you happen to live in the, if you happen to live in the houses, and per convenience you only ask the people around you, you would not get a representative sample. Does that make sense? Does that, I
Yes,
guess
sir.
that does that make sense?
Yes, sir. Yes, sir.
I mean, it's something that is not done very well in general. Okay, and I think this is why election polls are very bad, typically in India. They don't actually, precisely because they don't do this thing. So the question of what is a truly random sample is very, very difficult to to determine beforehand. But the best you can do is well, in fact, the absolute best you can do is to take a sample that basically shrinks the entire population. The proportion of people in that sample, the different types of people within that sample, must be proportional to the whole. Okay, so for instance, let's say I'm trying to ask, let's say I'm trying to sample, let's say I'm trying to determine the the different proportions of religions in India. Okay, then maybe this is a better example, right? So I want to determine how many people identify as Hindu, how many people identify as Muslim, Sikh, Jain, Christian. Okay, how would you do that? And I can only ask, and I'm only doing this from a sample of 1,000 people. Then I had better take in my sample something close to the real fraction. I mean, there's no point me going to a madrasa or like a church and doing the same thing, because I'm getting it wrong. My sample will be skewed. So I must, in order to get a truly random sample, I must sort of ask people from the localities with the okay. So this is not a good example because I'm assuming the thing I'm trying to determine. But to get a truly random sample, but let's look at this. I mean, I think this example really brings it out well, right? So in Mumbai there are 2,000 slums, okay, and in the north of Mumbai there is very different geographically than the south. There's a big national park, if you've ever been, Sanjay Gandhi National Park, right? There's lots of green space, and so the way the localities are separated is very different than in the north and in the south. I know for a fact that these numbers are not true up north, okay, but they were true down south. Why? Because these samples only looked at some small number of these widely separated slums. So had they gone over all over Mumbai and looked at all of the slums, then that number would have come much more to the true value, which is probably a lot less. Okay, so random sampling is, I mean, I'm hoping it's common sense, but we have to really think about it, right? So the idea is that you really want to have some fraction of you want okay. So maybe the best way of saying is if you're trying to determine something, you want within your subsample, you want the fractions of various types of people or localities or anything within that that sample to be the same as in the whole. Okay, so if you want to ask, if 10% of people in your village live in a slum and 80% live in houses and 10% live in a railway colony, then your subsample had better contain, out of 100, 10% people from the slum, 80% from houses and 10% from the railway colony. Okay, so 10, 80, 10, right? Okay. So so part of the question was, is this only true for normal distributions, the Gaussian distribution we saw before? So these are very separate concepts, okay? But it turns out that if indeed the underlying distribution is Gaussian, that means it's centered around some mean, and there's some standard deviation around it, depending on the size of standard deviation. Let's say you're doing election polling, which we'll cover in the last example. In fact, you don't need a very large sample to get a very high degree of accuracy. So if you only want a few percent accuracy from the true voting intention of the population, you only need to poll several thousand people in a country of 1.3 billion, if the sample is suitably random. Okay, so if indeed it was a truly random sample of Indians, right, And by that, I mean, you really, really, take your sample in proportion to, okay, so this is probably only useful for state elections, right? But you take it in proportion to the number of people, of different localities in your state. This is enough. Several thousands, like 10,000 or something, to get within a few percent of the true underlying voting intention. So, of course, if you take more and more people, you're going to get more and more accurate. That polling error gets less and less. But you're going to have to do a lot of work to get it down to, let's say, 0.1%. That's in fact almost never. I mean, you're going to have to take you have to take the election at that point. And that convergence, the convergence to the true voting intention as a function of sample size, is quick. If it happens rapidly, the sample size you need is not very big if the underlying distribution is normal. But if the underlying distribution is, let's say, it has some large outliers, it has a fat tail, then indeed you can be misled, and in fact it'll take you a very long time to get to the true distribution. And by the way, this happens all the time in economic forecasting or financial forecasting, right? There are all sorts of stock market crashes and all these things, and people are like, oh, we didn't know it was coming. Oh, we lost lots of money. It's because people were fooled by randomness, right? They didn't realize. So the stock market doesn't follow a Gaussian distribution. There are rare fluctuations that causes crashes or causes, and so if you're trying to understand an underlying trend, what is happening over the next, over the last few months of this? Let's say the stock market is, constantly going up. Okay, so we look at the stock market today, we look at the stock market tomorrow. No matter how many samples you take, the stock market is not always going to go up, or it's not always going to go according to some fixed pattern, because there are very large but not super rare fluctuations. And so this is an example of how you will never converge to the true, because I mean it doesn't exist for the stock market. But another example is the following thing, right? No, maybe I'll stop here. Maybe it's getting a little too complicated, because I really I want to finish in time for some questions. But nevertheless, the idea that the sample has to that the sample has to be random is the higher quantity of the sample, the more random your sample is, the more, if you like, the more representative your sample is of the true population. Okay, so if you want to think of a random sample of the true population out of 100 Indians, if you're just talking about, if you want to sample, if you want to have a true population, if you're looking at voting intentions, out of 100 Indians, you want 14 of them to be Muslim, but among the Muslims, you want, the right fraction to be Bora, the right fraction to be Sunni, the right fraction to be Shia. If you're 80%, 80 whatever, 78% of the so-called Hindus, then you want, the right, caste, regional, if you can cover a sample that has a large enough number where that is accurately represented, and each type of person has a big enough sample, I imagine for the entire country that's no more than maybe, I don't know, a couple of tens of thousands of people, then you're in business. But that's typically not the case. And so what we come across is the notion of estimating values of the underlying thing that's happening using only a finite number of trials. Okay, so back to the matter at hand. Okay, so what we were trying to do, recall, was we were just trying to get the estimate of the number of infected people with a test with a known sensitivity, okay, and some way of determining this quantity, the number of people infected given that they tested positive. So if we have some subsample that tests positive, okay, then we can obtain this number by within that subsample, just maybe subjecting an independent test or doing lots of repeated PCR tests to the smaller subsample. There's still a manageable number of tests. We can estimate the number of infected people given a prevalence. We can estimate the prevalence given an estimate of this quantity, and we estimate this quantity from our sample. Okay, so we use our sample as an estimator. We take a finite number, let's say 100 people, and if they're random enough, and we find that 3 or 4% of them are positive, we can extrapolate the entire population using Bayesian. Okay, but that requires good enough random sampling. And so this is precisely what so I live in the Netherlands, and this is precisely what the Dutch government does. Okay, so this is a graph that's showing. So this is actually today. Well, so the data is a few days out of date. The population of the Netherlands is 17 million, by the way. So if you have 170,000 people that are currently infectious, that means 1 out of 100 people are infected. Okay, how did they determine this? Precisely via Bayesian reasoning. Okay, and so what they do is they just do random population sample. They just find a random sample in the population. They do a random COVID. So normally people that report themselves to testing centers are not random. Okay, they are not a random subsection of the population. They have symptoms. That is not random. Okay, so in order to do this, they must really just find random people off the street and say, hey, can you come in, do a test? Okay, fine. Knowing these two numbers, they can then estimate the number of people that currently have COVID. And so how do I use this information? Okay, so first of all, that information is obtained using Bayes' theorem. So how do I use this information myself? Well, at this point in time, I know that there's about 170,000 people currently infected with COVID. So that's about, I don't know, about roughly 1 in 100. So then I figure, okay, with the strain that's currently going around in the Netherlands, if I spend more than 20 minutes so it's quite quick now. If I spend more than 20 minutes in the same room, closed room, with somebody who is infected, I will also get COVID. So I have stopped taking trains. Okay, I use this, and by the trains in the Netherlands are much more not crowded compared to India, right? So let's say my office is in a town 30 kilometers from where I live. So I have a 40-minute train ride. On that 40-minute train ride, if I go off hours, there's like 5 or 6 people in my train carriage. If I do that twice a week, twice a day, for a month, okay, and if 1 out of 100 people is infected with COVID, chances are I will get infected with COVID. So I've made the decision for myself not to go into work. I will only work from home. Okay, so this is how I have used Bayesian reasoning. Well, it's a combination of Bayesian and frequentist reasoning. Because once I've gotten this number that 1 out of 100 is infected, I've then applied something like frequentist reasoning, which is a bit sloppy of me, but nevertheless, it's good enough. I can use this information to make decisions that affect my life, which is, am I going to get this new strain, which is not something I would like to do. Of course, I have the privilege of being able to work from home, and so I can do that, but a lot of people don't. But something to note is there is a number which is given by this blue line, and then there are these uncertainties given by this dashed blue shading. Okay, why is there an uncertainty? We'll get to that in a second, but it's something to pay attention to. But I would also stress precisely these techniques can be used not just for COVID, can be used for many, many other things, such as what is the population of the wildlife that's out there? Okay, so how is it, do you think, that people know how many tigers there are out in the wild in India? Do they go and they count all of them? I mean, okay, maybe there's so few tigers that they can do that. But let's say elephants or a special type of bird. How do they do that? Right? It's not like humans. It's not like they live in a fixed place and you can just go and do a population census. They use Bayesian reasoning. They use exactly what we used, but they use this technique called capture recapture, meaning what they do is they capture some wild animal and they put a tag on it, let it go. Capture another one, put a tag on it, let it go. They keep repeating, and as soon as they start seeing, repeat it, and as soon as they start seeing animals with the tags already on them, and they see a frequency of recurrence, they can then use that information plus some Bayesian reasoning to get a very accurate estimate of how many people, how many animals there are out there. So this is not just applied to pandemics. This is applied in ecology. This is applied in in census taking. It's very ubiquitous. So that's not an application we'll go through because we're interested mostly in the pandemic. We have to just to finish this. We have to understand, why are there these errors? Well, it's pretty straightforward to see that if I have a formula like this, and there's some uncertainty in this quantity, and some uncertainty in this quantity, and some uncertainty in this quantity, then there must be some uncertainty in this quantity itself, right? We can't possibly know all these numbers to 100% accuracy. And so the the uncertainty in each one of them, or if you like, the error in determining these quantities, results in some error in determining the prevalence. Okay, and so knowing how to calculate how these errors affect this is called propagation of errors. This is a very fundamental uh, um, concept in statistics, and we will work through an example how to calculate this in the problem set. And so the error, if you like, in the fraction of positive people is really just a sampling error. Okay, so if I only did 100 tests, what is the, and I determined that, let's say, some fraction, let's say 50% of that fraction is positive. What is the error? What is the deviation from that fraction of the number of infected people compared to the full population? So that's a sampling error. So for a small population, for a small sample, that sampling error is going to be big. If I only took a sample of 2 and one of them is infected, I get 50%. But if I took a sample of 100 and then one of them is infected, that fraction is now 1 out of 100, right? And that's starting to get closer and closer to the true underlying fraction of infected people in the population. So that's known as sampling error. And so for election polls, so we will cover this example. We will cover this again when we do election polling, and we will find that in fact, for if you have a Gaussian distribution, if you have a normal distribution for an underlying opinion, and this is very important actually. So this gets back to the question that was asked: is this a function of the Gaussian? And the answer is no, because if you have a Gaussian, then indeed you find that your sampling error gets less and less and less for a larger and larger sample. But if your distribution is not Gaussian for some reason, then you need a much bigger sample to accurately estimate the true underlying population prevalence. And so this is maybe happening in India now, but it certainly happened in America when Donald Trump was elected president, and it happened in the UK when Brexit happened. The election polls were completely wrong. And they were completely wrong because the underlying population opinion was not a Gaussian, but it was multimodal. There were 2 humps that were separated. The population was polarized. Okay, so there was something that looked like this, and so that's why the samples were not good enough, and everybody thought that Hillary Clinton was going to win the election instead it was Donald Trump, because the sampling error was much bigger than they realized. Okay. So and so that's really the there's an element of having to really think and being really skeptical about the numbers you have in front of you. So this is part of the hazards of doing statistical analysis. You will never ever do anything to 100% accuracy, because there are always things you won't know, the unknown unknowns, as it were. Okay. So finally, we're going to just end up with something that I hope can be explained using just common sense, which is, and this is hitting on the concept of estimators and whether they can be biased or not biased. Okay, so we covered this in the first lecture. We're going to cover it again. So the question is, how can we estimate the case fatality rates of the disease? So what is the probability of dying of COVID-19 if you have been confirmed to have it? Okay, so it's a number of, so at any given time, the obvious thing to do would be to just take the number of people that are dead and divide it by the total number of cases. Okay, so I mean, that's precisely what you mean by the case fatality rate. So of course, at the end of the epidemic, if this goes to the end of the epidemic, then obviously that's the definition of the number, right? So it's obviously this estimator will give you the exact number at the end of the epidemic. So that is if we like, an unbiased, what we call an unbiased estimator. But during the pandemic, if we looked at any given time, the number of deaths at that time and divided by the number of confirmed cases at that time, it turns out that in fact it's a biased estimator. So we have to recall that that estimators can either be biased or unbiased. What does that mean? Okay, so let's say that you're trying to figure out the average of something. Let's say the average heights of all Indians, of all Indian adult males or adult females. Um, and of course, you can't measure everybody's height. So what do? You find n individuals from some sampling process. Then it's reasonable to estimate. The word is estimate the average by just taking the sum of the heights and taking the average of your subsample. Okay. Of course, as the sample size goes to infinity, it turns out that this estimator for the average really does go to the true average of the heights. So the estimator of the average really does go to the true average. It is unbiased. Now let's say you try to do the same thing for the mean square. Okay, so what do? You take you take the average you calculated from the last step, and you take the deviation from the mean, from that estimate of the mean, and you square it and you divide by the number of things in your sample. It turns out that in fact that this does not tend to the true variance. It is in fact biased. And the unbiased quantity actually has to divide by n minus 1. Of course, the difference is very little, as n is not, as n is very, very big. But nevertheless, it is we can maybe I'll put this in one of the problem sets. You can actually prove that this is true, that this is the unbiased estimator, and this is the biased estimator, even though this should really tend to what you think. This would be the definition of what the variance is, right? So we have to construct a way to estimate what the mean square is, but in order to do that, we have to estimate what the average is. Had we put in the true average here, this would not be a biased estimator, but we can only estimate the average. Okay, so because we're putting the estimator, it turns out that this is a biased estimator, and so therefore we have to divide by n minus 1 to unbias it. So in this example, it turns out that this is a biased estimator. Okay, at any given point in the epidemic, the number of deaths divided by the number of cases is going to bias the case fatality rate. And the claim is that, well, okay, but the claim is that in the beginning or the middle of a pandemic, that this is more biased, and that this one is somehow less biased. This is getting closer to the true case fatality rate at the given time. And can anybody guess why this might be true? The reason is because during an epidemic, there are lots of cases that are still ongoing. Okay, and there's some diseases, the outcome takes a long time to resolve. Okay, so it's not always that a case ends up in a death or a recovery. There's a large amount of cases for which it's still ongoing. We don't know. So in the middle of of course, at the end of the pandemic, everything is resolved. Okay, so that's no longer true, right? So the number of cases equals the number of deaths plus recoveries, right? At the end of the pandemic, this is equal this. These two estimators converge to each other. But in the middle of a pandemic, there's still lots of people who are unresolved. Okay, some people have had COVID for months. Okay, so what we should do is we should remove them from the number of cases. And in doing so, we find out that the estimator very quickly becomes unbiased. And so here is, of course, SARS has now lasted for more than a year. But for some epidemics that last only a few months, and there have been many of these in the past. So let's say from the first SARS epidemic, which is for the virus SARS-CoV-1, the current epidemic is SARS-CoV-2. From the first, so SARS means severe acute respiratory syndrome, coronavirus 1. The current COVID-19 is the same thing, but coronavirus 2. It also originated from the same region of southern China and in Hong Kong. Well, it originated in southern China and then spread to Hong Kong, unfortunately, and then via Hong Kong through to Canada, much like the current pandemic. And what we have is that if we look at, so this is a very short pandemic, in fact. This disease was so lethal, and it was so contagious and it was so lethal that it didn't actually have too much of a chance to spread. And of course, quick action by the Hong Kong and Canadian health authorities really put an end to things. It wasn't clear what was happening in China because at the time, which is around 2003, it was harder to look into what was going on in China than it is today. But indeed, it looks like all the right actions were taken at the right time, and that epidemic ended pretty quick. But okay, so this plot has a lot of information on it, but all you have to focus on is this. These black rectangles are, if you like, the observed case fatalities. This is the quote. This is really the right answer, if you like. And the black diamonds and the black rectangles are the two simple estimates that we had for the case fatality rate. So this one corresponds to the triangles. This one corresponds to the diamonds. And as you can see, the triangles are getting closer and closer to the black dots. So being able to interpret a plot like this is also a very useful skill. So what's going on here is that we have one estimate calculated at any given time given by the triangle. This is the improved estimate. As you can see, it's getting much, much closer to the true estimate than the sort of the simple one that we had before. But of course, as time goes on, they both start to agree with each other as well. There are other estimators that they use that are a bit more complicated that I won't go into, and all of them come with, if you like, error bars. Okay, they come with statistical uncertainties that comes from not knowing precisely what these numbers are because they're subject to lots of uncertainty themselves. So it turns out that the improved estimator of the number of deaths divided by deaths plus recoveries is much better at the beginning and the middle of the pandemic than just this estimator. So estimating the case fatality rate of a disease requires picking the right estimator as well. So with these three concepts, so we've answered three different questions today that have brought up some very interesting aspects of statistics and data analysis that we've covered in our lectures that we've applied to the pandemic. And one of them is the application of primarily Bayesian reasoning to the pandemic. And we've understood that you should be very skeptical of how you interpret positive test results given a particular population prevalence. You've understood how to estimate a given population prevalence using random sampling. And we've also understood in a much more real case, a much more applied sense, how estimators for certain quantities that you're interested in can be biased or unbiased. Okay, so here are all the core concepts at the bottom of the page that we've covered in just 2 lectures, and these, hit some of the more important concepts in data analysis, all with nothing more than 10 standard mathematics. Okay, so, but that doesn't mean that it's simple stuff. It's quite deep. Okay, and so you have to think about it. Okay, so any of the concepts I spoke, please go away and think about it. And so if you're wondering what does he mean by random sample, well, think about what it means for a random sample. And the way to do that is to ask yourself the question, well, what if work through an example, right? And the way if you work through examples is to consider very different cases, right? And so you have to sort of internalize all of these concepts for yourselves. And so what I'll do is I'll post a problem set. We'll work through a bit more of this Bayesian reasoning stuff, and hopefully you will see, you will through example be able to hopefully try and apply some Bayesian reasoning to other things other than the pandemic, and maybe even apply them to your own lives. This concludes the two-part application to COVID-19. Next week, Ramiz will begin by focusing on the problem of fraud detection, and then after that, I will come back and we'll go to the application of election polling, where we will really study this question of sampling much more carefully. So that is the formal lecture for today. So it's maybe now time to stop and maybe take some questions, if you have any. Okay, so if there are well, take your time, think about any questions. But if not, then We will have a Q&A session on Friday, and I will post a problem set later today. Try and do it, and then we will work through an exam, and then I will work through that. We'll maybe work through some of those problems in the Q&A session. So this was, potentially, potentially a lot, potentially not. Maybe I'm going too slow for you guys. It's hard for me to tell. But I hope you got to see, some of the utility of Bayesian reasoning, and how how profound some of the implications are for something as simple as testing. And so, if there's one thing you remember from this lecture, is I didn't just tell you without and just assert it without facts. I gave you I hope I gave you all the tools for you to understand for yourselves why it is that if you go to a doctor and the doctor says your family member has cancer, how you should almost certainly always get a second opinion. Because from Bayesian reasoning, you know that it's usually quite unlikely that the person actually has cancer, depending on the underlying prevalence of that type of cancer. If that cancer is quite rare, then it's almost certain that it's going to not be the case. But if that cancer is quite common, then it becomes more and more likely. And all of that follows from stuff that you should be able to take away and understand for yourselves. Okay, so maybe I'll put in a real life example in the problem set as well for you to really, internalize that take home message. So we have a few minutes for any questions if you have any.
Sir, in first few slides, the formula you showed, sir. Can you show that again? And
Yep. Yes.
Bayes theorem, Bayes formula.
Yep. Give me a second.
सर वो बेस फार्मूला एक बार थोड़ा सा एक्सप्लेन करेंगे.
This formula.
Yes, sir.
Yeah.
And now
this is base
yes.
formula. Yes.
Yeah. Now in next slide you converted that into specificity and parameters. So उसको थोड़ा सा sir.
Yes, of course. Okay, let's do that again. Okay, and now I really would like to emphasize just how much of this is just common sense. Okay, but you have to not be.
Okay.
You have to not. No, wait. But you have to not. But it's hard. It's common sense expressed in a very strange language. That's why it looks complicated. So you have all the tools to understand this if you get comfortable with the language. Now it's written in a language that makes it seem more complicated than it is. So that's why this is exactly what I like doing. I like to spend again and again, this again and again, because only that way we really understand. Okay, so let's do this. Let's explain this slowly from the beginning. The idea of Bayes theorem is that if two things are going to happen, okay, the probability that event X and event Y happens, right? Means if the probabilities are independent, by the way, if they're independent probabilities, okay, like here, right? Like if they're independent probabilities, like you throw two dice, one after another, right? Then the probability of both of let's say I roll a 6 on one dice and a 2 on another dice, because these are independent probabilities, it's just the product. Okay, so the probability of finding both, that when you roll 6 on one dice and a 2 on another dice, is just the product of the probabilities. So the probability of both rolling a 6 and a 2 from two separate dice is the product of the probabilities. But it's not always true that probabilities are independent. Okay, so the example here is when you play cards and and somebody says, what is the probability of drawing a queen? And then after drawing a queen, what is the probability of drawing a 4? Okay, so we can figure that out. The probability of drawing a queen, if it's the first card you pull out, is 4 out of 52. But then the probability of pulling out a 4 is 4 over 51, because there's one less card. So it's not equal to the product of the independent probabilities. But if I drew both cards from two separate decks, then again, it goes back to being equal to the product. Okay, so we denote this by conditional probability. Okay, so the conditional probability is saying that if both things are going to happen, okay, what is the probability of, okay, I don't know, let's say, what is the probability of India winning the 2020 World Cup, and, um, you know, um, um, I don't know, and I don't know, Rishabh Pant hitting 6 sixes in an over, okay? Maybe they're not totally independent, okay? Maybe he does that in the final, right? So, so the probability of India winning the next 2020 World Cup and Rishabh Pant hitting 6 6. Oh no, let's make it more sensible. What is the probability of India winning the next 2020 World Cup and Rishabh Pant having an average of over 50 in during the World Cup? Obviously, if any batsman is having an average over 50, then this means the team is probably doing well. Okay, so they're not necessarily independent probabilities. So, so let's say we're asking for the probability that both India wins the World Cup and Rishabh Pant has an average of over 50. Now, if both of them are true, it must be the case that that probability is equal to the probability that India has won the World Cup, given that Rishabh Pant has had an average of 50, times the probability that Rishabh Pant has had an average of 50, or the probability that Rishabh Pant has an average of 50, given that India has won the World Cup, times the probability that India has won the World Cup. Okay, maybe that's a little too abstract. But maybe that's not a good example. I mean, of course it's true, but I'm not sure it helps. But the statement is that if any two things happen, okay, if two things happen, right, both X and Y have happened, that means either if X and Y have happened, that means that it must be the probability that X has happened, that given that Y is a certainty, times the probability that Y has happened, or vice versa. Okay, so please just say it out aloud to yourself again and again and again, because it could be nothing else. There's almost no mathematics in here. It's just saying if two things happen, then either this has to have happened given that this has happened, times the probability that this has happened, or vice versa. Either this has happened given that this has happened, times the probability that this has happened. Okay? It's just saying, and if they're independent, then it's just saying the probability of X and Y happening are just the products of these individual probabilities. Okay, so maybe I'll set a problem set where we deal with conditional probabilities a bit more. Okay.
Sir, is it like, sir? Is it like, sir?
Yep.
So
Go
is
ahead.
it like that in probability of Y, given that X has happened, multiplied by probability of X? So probability of Y given X, that means given X is that the condition of X that must be happened.
Correct.
Otherwise,
Yes.
means that is the essential condition.
Yes. In that case, yes. Right. So exactly.
And vice
So
versa.
indeed. So
Okay.
and vice versa, right? And they have to be the same, right? Right. If two things happen, right? If both X and Y, then this has to be true. This has to be true, and vice versa. This has to be true. Okay. Because in both cases, both X and Y have
Okay,
happened. Yep. And that you just divide through, and that's base theory.
okay.
So indeed, okay, so that's base theory. And it seems like, okay, well, that's fine. Okay, that's just rearranging some stupid equation. But the power is when you apply it to something. Okay. So we are interested in the probability that you are indeed infected given the condition that you have tested positive. Okay. So if we just apply that same logic, okay, so we know just from the same the same reasoning here, right? Is that the probability that you are infected under the condition that you've tested positive times the probability that you tested positive has to equal the probability that you are positive given the condition that you're infected times the probability that you're infected. And all we did was just stuck in numbers for what this is. And we thought about it and we put in real numbers, right? So so how we proceeded was so this quantity here is known as the test sensitivity, right? And so that's some number you read off the side of the box on the test. It says that If you're infected, there's a 95% accuracy that the test will be positive. And then I said, let me just say that you imagine 1% of the population in your locality is indeed infected. So that's given to you as 0.01. And all that was left was to estimate what this positive test result fraction was. Okay. But what we did was we thought about it and we said that the probability of testing positive, well, there's only two possibilities that are mutually exclusive and complete, right? Which is that either you're infected or you're not infected. There's no other way, right? I either have the disease or I don't. So the probability of positive tests is the probability that you test that either you're positive on the condition that you're infected times the probability that you're infected, or that you test positive under the condition that you're not infected times the probability that you're not infected. So this is just the, if you like, the definition of what this is, right? So if we put this into the bottom of this equation, we realize the common factor here and here. So we just divide the top and the bottom by this factor. We end up with this equation. Okay, so it's just taking Bayes' theorem and unpacking things. So this is where it gets a little complicated, but it's nevertheless, it should still be, you should still be able to trace back and think through from common sense what all of this means. And we now know that, okay, well, so now how do we determine these quantities? So we're given what this number is. We're saying that 1% of the population is infected. This is just a test sensitivity, which is the probability that an infected individual indeed tests positive. And we know that if the probability of being infected is P of I, then the probability of not being infected is 1 minus that. So we know what this factor is. And of course, the probability of testing positive, given that you're not infected, is of course the false positive rate. And that is just given by 1 minus the specificity. Okay, 1 minus, which the specificity is what is the probability that you test negative given that you are healthy. So 1 minus that is the false positive rate. So if we just put all of those realizations of words into the Bayes formula, you get this formula. Okay, so please start from here. Just think about what this equation means. Okay, it should be, if you just think about it in your mind, it should boil down to common sense. We will work, so conditional probability, so it's common sense, but written in a very complicated way. Now, the reason mathematics works is because it takes many, many different situations and it boils them down to the same abstract formula. So it looks complicated, but in fact, it's the opposite of complicated. It's very simple, but it's simple in a way that we're not used to dealing with. So it looks hard to begin with. But once you practice and you get used to it, this becomes the easiest thing in the world to do. And all it takes is practice. Everybody can do it. Okay? We are going to do it. And so if I just follow through this common sense observation, right, and I divide through, and I get Bayes' theorem, and I just put in what I mean for all of these quantities, I end up with this formula. So we apply this to what we know from COVID. So let's say you have 95% test sensitivity, which means that if you're positive, if you're indeed infected, there's a 95% chance that the test says positive, right? That's test sensitivity. And test specificity, which is 1 minus that, is the false positive rate. Okay, so 1 minus this number is the false positive rate. So 5% of tests that are positive will not actually have, which will not actually have the sample has COVID. This is the probability that you are indeed infected given that you tested positive. So if the prevalence is 0.001, you put in these numbers, you get 0.16. Okay, so for one test with an underlying prevalence of 1%, there's only a 16% chance you actually have COVID. There's an 84% chance that you're not infected. So this is all formula, but let's think about why that is. Okay, why that is that really that there's only 1% of people out there that have COVID, but if your test gives a 5% false positivity rate, right, that means it's 5 times more likely to say that somebody has COVID than actually has COVID. So therefore, it shouldn't be a surprise that a positive test result is most likely to be wrong. Okay, so the way the lab proceeds is that it just repeats. So it just says, okay, well, this is so if you've tested positive, there's only 16% chance you actually have COVID. Let's just do the test again. Okay, And by the way, this is just to emphasize that even with very, very accurate tests, still, if with 1% prevalence, you can only be 90% sure. And as the example here that we showed was with even 97% sensitivity, 99% specificity, only a 1% false positive rate. Let's say for a cancer diagnosis, you're only, and the prevalence is, let's say the prevalence is 1% of the population has this type of cancer. There's only a 50% chance that the diagnosis really does mean cancer. And so, what am I trying to do? Why can't I show this full screen? Okay, whatever. Here we go. Yep. So you know, with COVID, you can run the test many times, right? Whereas with the cancer diagnosis, you can probably only do it once, and either you send the person to chemotherapy or you don't, and chemotherapy could kill you. So be careful, right? With COVID, we have no such downsides to testing again or treatment. So and so the idea is that, you know, if indeed you know, it turns out that, you know, you only have a 16% probability of actually being positive, given the positive, you know, given a 1% prevalence, given a 95% specificity and a 95% sensitivity, you just do the test again. But now the prevalence is not that you're in the 1% of the general population. The prevalence is now truly 16% of the samples that are tested positive. So now the population is now a subsample. Those tests that have already tested positive, of which 16% are indeed truly infected. So the prevalence is now 16%. So when you repeat the test twice, you get that 2 tests will give you, so you just stick in the same formula, but now with 16%, and you get that 78%. You have a 78% chance of being positive. You do it 3 times, and it's 98.6. And if you want to be more than 99% sure, you have to do it 4 times. Okay. But if the prevalence was very bad, let's say you're in the middle of an epidemic and in your locality, let's say almost 1 in 3 people have it, then just doing 1 test means that that the probability that indeed you're infected goes up to 89%. And again, if you ask yourself, why is that true? Well, if your false positive rate is 5%, but you know that 30% of people are indeed infected, then it is much more likely that this is a true result. And you only know this by doing this by Bayes theorem. So after 2 tests, you're indeed above 99% accurate. Okay, and so this is why perhaps it's sensible at the beginning of a pandemic not to necessarily over-test or to overdo mass testing. Or if you do it in localities where the prevalence is actually quite high. Okay, so I hope that makes it a bit more clear. So as we went through this, if you watch the lectures again, you will notice that everything that I've said at least 3 or 4 times, right? And the reason is because it's not because I forget. It's because this takes getting used to. And you have to do this for yourself, okay? Don't listen to me. Do this for yourself. If you want to go and learn a language, you don't just sit here. I mean, you can't learn a language just by reading. I mean, you can learn it to some extent. But to really be able to master a language, you have to go out and you have to speak it. You have to go out and you practice, blah, 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 right? So I'm doing it right now with Hindi, okay? So I understand Hindi, but I can't speak it. Why? Because I never speak Hindi to people, right? I only speak Marathi to my family and my friends, and I speak English otherwise. But now that I'm speaking Hindi more and more, it's getting more and more, getting more used to it, right? So I'm asking you to do the same thing. Go away and speak mathematics. Do this yourself. Do it yourself. Speak it out loud. Work out examples for yourself. Only then will you really understand this stuff. This is always how it works. It's like Kung Fu, okay? I use that example again and again. You will never learn from just passively taking information. You have to go and you have to use it. You have to practice. And then once you practice enough, you start to understand it. So, so that's why we will be doing problem sets. We will prepare problem sets for each one of these lectures. And try to work through them. So yes, so we have a few more minutes left. We have time. We have time for one more short question, if any. Okay, so if there are no more questions, then please keep updated. Keep so all of these lectures get posted online. The slides will be posted online. You can review the material yourself. I hope you're already starting to see how interesting some of the applications of some of the abstract things we've learned can be, and immediate, um, and potentially life-saving. So please study the material. I will post a problem set either later today or tomorrow, and then on Friday we will have a Q&A session where we will work through some of these examples, and then next Monday, Ramiz will begin a lecture on fraud prevention. But other than that, if there are any questions that you still have that you didn't get a chance to raise here, maybe the connection wasn't good enough or you didn't get the opportunity, please just email me. You should have gotten an email from me on so you could I gave you my Gmail associated with this with Nalanda Academy. Please just email me and you can ask, and I'll do my best either to reply to your email or to raise it in the next lecture or to answer in the Q&A session if I see in the Q&A session. Okay, so this concludes our first application, our first of 3 applications of data science to COVID-19. These are all theoretical applications because at this point in this module, we're just trying to get you comfortable with basic concepts. Okay, the next module will be much more hands-on. We will really do some examples, but we have to first learn how to crawl before we learn how to walk. So you're still learning how to crawl. But unlike babies, I hope you can tell this is not baby stuff. This is really, really serious stuff. Okay, serious stuff that serious people get wrong. Okay, so I hope you see that this is very, very useful techniques with which you can make informed decisions about your lives. Okay, and if you're in any doubt, please just go through, think about this example of what a cancer diagnosis really means, and you can see. Unfortunately, our doctors have to learn so much. I feel bad for them that not a lot of them have time to learn statistics. But if you now, because you know statistics, you should know very well that depending on the underlying prevalence of a particular cancer in society, it can often be the case that a positive cancer diagnosis is not necessarily correct. And now in the West, what's happening is that they're discouraging doctors, they're discouraging people from getting cancer tests, cancer diagnostics too early, because they're realizing that they've been killing more people by the treatment than actually the cancer itself. So there you go. Okay. So I will end here, and please work through the problem sets, and let's connect again on Friday. And have a good week, everybody. Jai Bhim.